Let's power up the system. So you're going to have these two white panels. These are newer to Varian, and these are the main circuit breaker panels. You got one for the OBI, which is for these arms, and then you got one main panel for the rest of the machines. Usually these are in the console area, so you'll find those out by the treatment machine or by the door, someplace like that. So they'll give you a startup procedure when you, on your location, they'll tell you how to reset this breaker. It has the emergency off buttons are tied into this breaker. So when you hit an emergency off, it'll trip this off. So a lot of times if you can't start this breaker, it's because one of the emergency off buttons is pushed in. And Varian has it to where they originally had it to where you needed 2 people to start the machine. So you had to go into the modulator, hold the button in there, then you had to push this button, which will let you reset the breaker and turn it on. Now they have a one-man system where you go push that button. It has batteries in it, so then you can come over here and reset the breaker by itself. Sometimes those batteries fail, so I'm not telling you to put tape on that start button, but you always want to remove the tape on the start button because that disables your emergency offline. So that's how you start the machine on. This one's 208 in the United States. It may be 240. This one is 480, and that's for your X-ray tubes. So that's where we start to turn on the machine. Then we'll come over to your modulator. So this is an older modulator. It's what we call the tall one. So down here at the bottom, this is your 120 volts or your 208 volts to get everything working. Over here and on top, this is everything that produces your high voltage to run your klystron. And this is about 25,000 volts coming off. It hits a pulse transformer in the bottom of this. So when you're treating the machine, you hear the bzzz. That's that pulse transformer at the bottom. And that's applying high voltage to your klystron, which is roughly 127,000, 25,000 volts. That's just what it takes for that power tube to amplify your RF power. So on this system, this is where you will do your maintenance. You can come around here. So for you guys, you'll always check the morning. You're going to check some temperatures up here, and the temperature gauge is on this one. On a Kona stand, has a little gauge right here, usually a window in the door, so you don't have to open things up. But if your water is low, you're going to have to fill the water up. You'll get a water interlock or flow interlock where it shuts your pump down if the water is low. So that's one thing we ask you to check. Another thing, if your machine is shut off, all these circuit breakers, I have them shut down because this isn't a high energy producing machine, so it just generates a lot of heat. Over here in your modulator, you'll have circuit breakers down here on the bottom. So a lot of times we'll ask you, go check and see if maybe your motors on your couch isn't working. So I say, well, go see if your motor breaker is on. So those are, we'll guide you to areas of the machine that are safe for you to touch to go check stuff remotely. The rest of the modulator, you shouldn't have to play in there. You shouldn't have to take off any covers There's always safety covers. So any place where there's high voltage, there's going to be a safety panel covering it. Now we might ask you to grab a flashlight and look in through the screen, see if you see anything burnt or whatever. A lot of times if you're in smaller departments, your engineer could be 3-4 hour drive away. And so a lot of times he'll have you look at stuff, you'll be his eyes, and he'll order parts before he even leaves to drive out here. So maybe those parts will be drop shipped, they'll be put on a plane, they'll get there that night. So sometimes we'll ask you to do stuff, but anything we ask you to do would be done safely. And you heard the click. What that is, it's a crowbar in the system, and all these doors have an interlock switch on it. So when you open the door, it prevents any high voltage from being made. Another thing that we might have you ask or look at is your system is cooled by water. It's either going to be cooled from the regular tap and it's going to be flushed down the drain, or it's going to be attached to a chiller system, and that's save water. So we might ask you to look at these gauges to make sure that there's readings on those gauges, and we might say, well, it sounds like your machine is overheating. Maybe you should call your chiller engineer or your facilities engineer. Make sure there's water to the machine. Make sure the chiller is operating. We always joke that these are very good, inefficient water heaters. So we operate the machine at a constant 40 C, which is a really nice hot tub temperature of about 104 Fahrenheit. So we do that to cool areas of the machine, and we also heat areas of the machine. So everything's at a constant temperature. So you'll have water pipes all through the machine. Your guide has water pipes in it. Your Klystron has water pipes. Your target area has water pipes. There's water pipes in your bend magnet. So I'm mentioning a lot of water. So one thing we have you check before you rotate the gantry is to look on the floor and make sure there's not a puddle of water on the floor. So we have you park the gantry at a certain position. On an OBI machine, it's roughly 4 or 5 o'clock, and we ask you to rotate the collimator to 90 degrees. Why we do that is because if there's a water leak in the head of the machine, it doesn't drip into the electrical components. Because I just said they're pretty expensive, right? So if you rotate the gantry, one thing the fiberglass will do, those covers, they'll hold a lot of water. So when you rotate the gantry, now you put all that water into all your electronics. And it makes maybe an hour job to repair, maybe half a day. You rotate the collimator to 90 degrees if you have an MLC, a multi-leaf collimator. And that's so you don't have the gravity of the leaves pulling against each other. So you have it in a static position. That's why you rotate the collimator to 90. If you have just a system with a portal vision, we'll ask you to rotate to just 90 degrees because we don't have the issues with the OBI tube in that. If you don't have any of those components, some people just park the gantry down at the bottom. So that's why the gantry is parked in these positions. Sometimes we may forget, or you're in a hurry, or there's a service need why we need the gantry parked head up. And we'll leave you a note. Say, don't rotate the gantry, don't do this, we're still working on it, your machine's down half a day, or whatever. So let's go around to the other side. This is your Klystron, and I have the power supply is turned off, but a lot of times this will be really hot. It'll be hot to touch. Won't be hot enough to burn you, but it will be hot to touch. See this little note here from your varying engineer? This is your SF6 tank. And you have, usually you're gonna have a couple knobs here. This one's a newer style. Usually I have a great big black knob and everyone thinks that's the knob to open the tank to fill up to your gas level. Well, that's actually a regulator knob. So the pressure in this waveguide, this is the waveguide section here, we want at 32 pounds per square inch. If you go up to 45 pounds per square inch, I was talking about that RF window. You'll pop that window out, and as what you do is the guide is at vacuum. So when you get a vacuum leak, it sucks everything in. So it's gonna suck all your SF6 and all that beryllium window into your guide. And that's $250,000 to replace your guide. And you're down for a week and a half. So that's why we put these little notes on there. It'll be taped up if it's the old style regulator. So we have you open the valve on the top, the tank, and then this little black valve, we ask you to open that. This meter will fill to a certain point. Should shut off between 32 and 34. And then you close this and you close the other valve. Why we have you close the valve, it's designed to auto-fill. You won't know if you have an SF6 leak until your tank's empty. So if we have you close the tank and only fill it when you need it, then you can tell us, he goes, well, I'm adding gas every morning. Well, that's too much. That means you have a leak in one of these flanges someplace. So your engineer will come out and he has a detector. He'll sniff around for that leak and then he'll probably replace a gasket. So that's why you write these numbers down when you do your morning check on a variance system. Siemens and Electa, theirs are a little different on what you'll do to warm up the machine. Some of the other things you'll look for, you always want to look for fluids or stains, water stains. I mentioned before, you might have that oil leak. Like this one has. It has some residue here, so they probably opened this cover to do some maintenance, and you'll have a little bit of this oil residue. And it's like one drop will spread 5 miles. It's really thin and viscous, so it'll spread a lot. If you spill it on your tile, eventually it'll get underneath the tile and it'll dissolve the glue. So you always want to tell your engineer about any oil leaks or any water leaks on any of these fittings, any drip discoloration. If it's copper and there's water, it'll turn green. So those are all things you need to look at as you're getting information for your morning check. Okay, we talked about your emergency offs. This style of door, if you close the door too hard, this is just a spring button that activates this one. So if you slam the door, it's a little flexible, you'll shut the machine down. Which isn't a big thing, but it puts you back 15 minutes to go through standby and warm up and all that. So we mentioned the couch and pinch hazards. You'll have a lot of warning stickers here. You don't want to grab it from underneath. This one has a plastic underneath. That was one of Varian's modifications to keep you from grabbing it underneath and sliding it back and forth. If you use a lot of linen, you'll see a lot of dust buildup on these rails, those are things where you want to tell your engineer if you see a lot of dust in your room on top of the modulator. All that dust also gets into the components. So you might have a maintenance problem in your facility. They need to change the air filters or something like that. If you have excess amount of dust, it clogs up the bearings and your couch doesn't move very well. So you tell your engineer that, hey, maybe you need to come in more often to clean the couch. This cover will drop down. It'll allow access in here. This is one of the things we inspect. So when we come and do a PMI on the machine, and PMI is preventive maintenance or inspection, that's what that stands for, we'll remove all the covers. Most of your engineers, they like to spend most of their time with a flashlight and their eyeballs, and they're looking for cable wear, they're looking for signs of water leaking or oil leaking or maybe your gas leak. They'll record how many times, or if you tell them how many times you're adding gas to the system, that tells them there's a leak. One of the things that Varian did is this display in the middle. Someone thought it looked like a pizza, so we call it the pizza board. So your Varian engineers, they're going to say, well, it's behind the pizza board. And you're like, what is that? So that's our lingo. Doesn't always communicate well with you guys. So, but we'll remove the covers. We'll do some mechanical movements. We'll do a lot of cleaning, so you do a lot of housekeeping. And then we do a lot of record and verify of voltages. So we want to see if there's any changes in the performance of the machine. We'll see a voltage change. Your modulator has a couple tubes inside there. They're called thyrotrons. And we measure a certain voltage on that tube. It tells us the life expectancy of the tube or when it's going to fail. And we want to replace it before it fails so you guys don't have downtime. So a lot of this stuff that we do is to prevent downtime from you. And at the beginning I said it gives a lot of stress to everybody in the department, your patients and your engineer. So your service contract is generally geared around the uptime of your machine, keeping it running. And that's why we do all the inspections and checks that we do. Let's go back into the room and we'll go through some of the checks briefly. Then I want to go through some of the QA checks that Varian recommends that you need to do, that your physicist needs to check before you're allowed to use the machine for treatment. So a lot of times we'll say, we'll write you a note because physics must approve our service before you treat on the machine. And you'll call your manager will call the physicist and goes, this is what the Varian engineer does or did, and usually he'll get a copy of our service report so we can look at it. Most of your engineers will call the physicist or call your department manager and tell them or text them what needs to be done before you can use the system for treatment. Okay? A lot of the checks we do quarterly, semi-annual, annual, and biannual. And a lot of that is greasing, so your gantry bearing, that's a very precise piece of engineering. When they first started building accelerators, they used the same type of bearing that was found on a tank because it has to be able to hold that weight, but it also has to move within 1.5 millimeters. So it has to move all that weight within 1.5 millimeters. Can't have any flexing in it. Well, you need to lubricate those bearings. Any component that works that's in a radioactive environment will degrade quicker. So all of the circuit cards in the room, after a while, will just deteriorate because of the bombardment of radiation. All of the plastic in the collimator, all those little tie wraps, all of a sudden they just start to disintegrate. Well, the insulation on your wires do the same thing. So older machines are a little bit more fragile than newer machines just because of the radiation damage. You want a new cell phone? Put it underneath the head of the machine and beam on for a while. Destroy all your electronics. So those are just things to be aware of. Why an older system might seem like it's down a lot more. It's because it's wearing out. And it'll get to the point where now you start doing refurbishments. You'll replace cable harnesses, major components. Your MLC, the variant system, your MLC has 122 motors if it's a Millennium MLC. And all the components, the electronics in that's the most, that's the area of the most intense radiation is right in your collimator area. So that's why we're going to go through replacing some MLC motors. And I'll have all of you replace a motor by yourself because you'll have to do it maybe in the field. Training machines are great for this. And we actually have a bad motor in there anyways that we need to replace. So we'll work on that. Any questions about the machine, why anything does what it does, or why we check what it checks? Okay, so with the inspection, I'll tell you certain test points, where to look at the voltages, where to measure them. Varian writes this up. So they have engineer speak, 2100. This is basically a 2100. We'll call it C1, C2, and C3. And that gives it a date range. So C1 is a 2100 that was the introductory product. So that was, go back into some ancient history. Varian made in 1800. It was an analog machine. It used high-low logic, a lot of relays. They introduced the 2100 as a computer-controlled system. It was still an analog machine, but the front end was controlled by a computer. So it would take all the data into the computer and analyze it for your fault matrix. So a C1 machine is that early vintage of the crossover. A C2 machine is a machine that had updated electronics. And a C3 machine is where you started to get into klystron linear mode, which helped improve the efficiency of the machine. You went into the Kona stand, so you had a different packaging of your components. So a lot of the components that I pointed out on this machine won't be in the same location on a Kona stand machine. And on a TrueBeam machine, they're either in a different location altogether or they don't exist anymore. Let's see. So let's go into what we call the beam quality guidelines. So this is what Varian recommends for any time we do any service on the equipment. What has to be checked before you can treat? The product codes, this is just what Varian calls everything. Product code 14 means a low energy machine. Product code 27 means it's a 2100. 29 means it's a trilogy or a 2300. Then you got different iterations of the machine. 54 is a MLC, 56 is an HD MLC. 08 means you have an OBI system. So these are just codes that Varian uses internally to track a product. So a lot of times some departments they'll name their machines. I was working in LA at Kaiser Hospital. All their machines had different Disney character names. So one machine was called Tinkerbell, and if you didn't use their lingo, they didn't have a clue what you were talking about on the machine. Now, Tinkerbell was a low energy machine, so if I said your low energy machine, they goes, which one? It's Tinkerbell. So you guys will name the machine. Up in Canada, they named all their machines after trees. Have you named your machine here? What's? So that's quite common. Sometimes you'll even have your patients name the machines. I don't know, some people will decorate the machine. They'll put scary face on it for Halloween or whatever. So when we're talking about stuff, you know, we'll call it the Linear Varian trademarked Clinac. That's a Varian name. So they're all linear accelerators. We just call them Linacs. OBI, those are your arms, onboard imaging. Portal vision is actually IPV, electronic portal imaging, EPI. MLC, multi-leaf collimator. I'm not quite sure what ICM is. Or ICVI, not sure what that one is. So, come up to a nice little table. So, your biggest service instrument here, our maintenance item, guide replacement. So, when I said you fill up your SF6 too fast, and you crack that window, goes into the guide. So there's a procedure on what you have to check when you replace a guide. You have to verify all your dose. So this is what your physicist needs to do. Your variant engineer or third-party engineer like me will go check all these things, and then physics has to go in and physically verify with either specialized test equipment, operation of the machine. So this one requires you have to do output versus rotation. What do you think that means? Anybody? So when you're generating your photons and you're measuring so many MU per degree or whatever, you're rotating the machine around, and we want to make sure that that output stays constant. So if you're at rep rate 3, you're at 300 monitored units a minute, has to be 300 going all the way around. If it's not, that means that the physical guide is in the wrong place, and they'll have to move that around to get that output to stabilize. Or we have some coils in there that will steer the beam a little bit to make that happen. Light field versus X-ray, or your light field alignment. You replace a light bulb, you need to verify that the light is still where it's supposed to be, because the light hits a mirror and you got the angles, so you could have your light field too big, which means it's not going to match with your patient setup. Or if it's off a little bit, it means your crosshair isn't in the physical location that the radiation isocenter is. So sometimes it's, I just got to replace a light bulb. Well, now you need to make sure that your crosshairs are still mechanically centered to your radiation isocenter. So when you're setting up your patient, you know, you want that dot there, you want the radiation to be on that dot as well. Another big thing that we'll do in service is we do your ion chamber replacement. Ion chamber has 2 different chambers in it. So it's a backup to your primary chamber. They have to measure the same amount of radiation, but they also measure different areas in your radiation plane. So you'll have plates that measure your in-plane or radial plane, and then you're going to have your transverse plane or your cross plane. It's going to measure those plates to look for symmetry. If that system should fail, then you have to re-steer all your energies. Physics pulls out their tank, and they have to recalibrate what MU1 is again, and recalibrate for your morning QA checker that you'll put on the machine in the morning to make sure that everything's symmetrical. So a lot of work is done afterwards, and that's what physics has to check. Even power supplies, if you replace a fuse in the system, sometimes those power supplies are critical systems that affect all your beam steering. So changing a voltage there could have an effect on all your steering parameters for your symmetrical beam. Then you got maintenance or stuff for replacing your mirror. I mentioned that radiation makes a lot of your components or plastics brittle. You have a mylar mirror inside the head to reflect your field light. Well, over time, that radiation will make that mirror really brittle. And as you go through dry climates and humid climates, different times of the season, that mirror just go poof, and you'll have silver electrically conductive shards go throughout your collimator. So hopefully your engineer replaces that proactively. But that's one of the things that can go wrong while you're treating. It's like, I don't see my field light. Well, it's not necessarily your bulb's out. You lost your mirror. And then any steering you do, you always need physics to check. Have you seen any physics QA? Do you go in over a lot of that stuff so you understand the electrometers and the scanning tanks and phantoms that they use? Yeah? Okay. So since we're going to go over the MLC components, the checks that you need to do when you replace a component, mainly for you guys, you're just going to replace a motor. So replacing a motor, other than maybe reinitializing, or yes, you will reinitialize after you replace a motor, the system has enough self-checks that physics say we don't need to do anything. But anytime you touch the machine, you should always let physics know. Let them make those decisions. I don't even tell a physicist, it's okay to treat. I tell them what I do, or what I did, and tell him what effects it may have on the treatment, and I let him make the decision on whether he needs to check more before he treats. So the components inside the system, so in this printout, now this is a, how many pages is it in here? Okay, so there's roughly 200 pages in this manual. So what I did for you guys, since we're just going to talk about replacing the MLC motors, I took out all the garbage in the middle. So I dropped it down to about 40 pages. There's still a lot of stuff in there that's extra, like your table of contents. In case you want to look at something else, these manuals should be on site. On every site, there's 2 copies are sent with the machine. So these will be on site. So I left some of the terminology that Varian uses, or what their symbols are that they use at the beginning of this manual, and then we went into an overview of the components. Since you're going to be working in the MLC, I thought having an overview of what all the circuit cards were and kind of what they do, that's in this manual, the computers and the controller. So this system has the old style controller, hence we just call it the old style controller. The newer style is called an LPC, which is a low profile controller. And it explains what the cards are in the controller. This is the low profile controller that you'll see on some newer system. Kind of tells you about what the lights are on there, what they mean, what to look for. Also on this one, there are some lights on here. Those need to be on and in a certain sequence to tell you that system is functioning properly. Now, I wouldn't expect you to know what the lights mean, but I might ask you to say, hey, can you go look at your MOTCOM board? You have two of them. Do you have a green light on it? Do you have a yellow light? Do you have any red lights that are showing? And then in your head assembly, so this is where we're going to be working. We're going to have a couple circuit cards in there. We're going to have two head transceivers. We're going to have one for the A side, one for the B side. We're going to have a motor driver board. So the motor driver board is behind the head transceiver, and we'll call those the sandwich cards because they're connected together. Going to have two optical receivers, and that is used in the alignment of the system. It also gives you a fault on the MLC that says leaf in field. So it's going to look, it has a infrared beam that it shoots across, and it looks for that beam to be broken. And at certain times of the MLC, the beam should be clear. We have two secondary feedback boards. Those are the boards that collect all the data from what we're going to call the soft pots. And there's two soft pots on each side. You have a target soft pot and a isocenter soft pot. What the FDA requires, so now you know why we have two of a lot of stuff, why you have two gantry pots, why you have two pots on your collimator and two pots on your jaws, is anything that has a dynamic treatment or anything that is moving while you're producing radiation has to have a primary and secondary feedback source to tell you the positioning of those items. The TrueBeam, they went to tertiary, so they have 3 readout systems on anything that's moving during treatment. So your soft pots are your secondary feedback or your secondary positioning for your leaf motors or your leaf position. And your primary is going to be the motor itself. We count how many turns are on that motor to determine what the position of that leaf is. You're going to have a power distribution board. We're going to have a head power supply. You're going to have a motor interconnect. And then on some of the circuit cards, we have little fans. So those are the components of the systems. This tells you where they're located on the MLC. I kept the little description on what happens when it initializes. You're going to see the hyperterminal. An engineer is going to say, well, what does a hyperterminal say? And that's that program that's running in the background. It's actually talking to the controller and to the head assembly itself, and it tells us what the leaves are doing. So this is that beam that I told you. You have an emitter on one side and your receiver on the other. you have two pickups, and it's going to see when it blocks the first one and it blocks the second one, and that's how the system calibrates the positioning of those leaves. So then we go back to a physics test or check. Anytime we change any components in this system, that means your leaf position is now different, or it needs to be verified that we put it back in the same spot. So that's what happens every time you initialize in the morning. It's just doing a quick check to make sure that your MLC leaf positioning is accurate. So let's go back in the room. Okay, to start off with, you're going to have your MLC cover will be on. It'll look like this. You have a spring latch and you have two screws. So originally Varian just had this spring latch, and there'll be a Allen screw behind it, so you couldn't activate it. Well, someone didn't get the spring latch on properly, and this cover fell off and hit a patient. So that's why there's now two screws on it. So you'll always make sure that you screw the cover down to the head. And then we still use the spring latch. You rotate it, see how this one has a mark on it? That tells you it's safe to take it off. So the components of the MLC, we said the power supply. We talked about the motor interconnect board. So these are all the wires that are on the motors. A soft pot. So this is a soft pot. What a soft pot is it's a variable resistor that has a membrane instead of wires. This is the sandwich board. You got your head transceiver and your motor driver. Below here you have your power distribution board. And then in the middle you have your service panel. A lot of times you're going to play with the service panel because you have to move a leaf. A leaf might get stuck. So if a leaf gets stuck, you go over to the A side or the B side by flicking the switch back and forth. You have two knobs here. This one's the 10s, this one's the 1s. So we'll do leaf 7, and you can move it. A warning with this board: when you move the leaf, it will move the leaf. So if you go all the way back and you're at its hard stop and you keep trying to retract that leaf, Varian built in to the leaves to protect the leaf screws, the drive screws, a little T-nut. And it's a little bit of plastic. That's what pulls the leaf back and forth. You'll break that nut. And so then your leaf will move freely. It'll slide in between the grooves without any friction. So that means now you have to replace the T-nut as well. So I always look inside the system. Up is moving in, down is moving back. I always try to move the leaves in. If I know that the leaves, not the carriages, the leaves are in, then you can safely move a leaf back. So you might have a leaf that fails initialization. A lot of times it's sticky, or maybe there's some lint or a little bit of oil in between the leaves. So you'll come in and you'll move the leaf by itself, put it back to normal so your lights are off, and then you go reinitialize in the room. See if that fixed your problem. So that's maybe 5 minutes worth of work. You didn't really do anything, but you just saved yourself maybe 2 or 3 hours of downtime. On this system, we actually have a problem with leaf B4. B4 is not passing initialization. I'm hoping it's just a motor, but it could be this whole this bank of this interconnect board. So we're going to replace the motor on that one, and then I'm going to have you each pull a motor out and put it in so you can feel what it's like. I have some a diagram that I'll pass out, a couple sheets, so you guys to see what the makeup of a leaf drive system is. You guys can share this one here. If you pass those around. So the components of the leaf system is you're going to have your leaf, you're going to have your drive screw. Right in here is that T-nut, and that's a fail-safe system. The older MLCs, they were metal, and sometimes the MLC would lose its brain a little bit, and you'd collide those leaves together. Well, because it was metal and the drive screw was metal, it would just mangle it all up and it'd destroy everything. So this one, they put in the T-nut breaks. That's by design. Then you're gonna have a spring, and we're gonna have a little coupler. So the coupler is what's attached to the motor and mates to the drive screw. So you got like a little channel, and you put that in there, so that's what's grabbing the drive screw to turn. It's that coupler. So that's the makeup of the system. On top of this is a little ball spring. And how Varian designed their MLC is all full leaves and even half leaves, your secondary feedback, and that little ball spring is on the top. All odd leaves, half leaves, are on the bottom. So a lot of times we'll say, which leaf is it? And you'll say, well, it's leaf 32. We goes, okay, we might ask you to pull that leaf out and replace that T-nut. If it's on the bottom one, that means someone has to physically pull the carriage off, put it on the table. This weighs about 80 pounds. So we won't ask you to do that. So that's why we're always, we'll always ask you lots of questions over the phone. That tells me how far I can have you dig into the machine to look at it. So Varian made life easier for us. They call these clues. What it does is it tells you the location of the motor per leaf. And then it also shows you where the connector is for that motor to drive each one. So it just doesn't go 1, 2, 3, 4, 5 across. It's kind of mangled slightly, but usually all these ones on the top are going to be for your top motors, are going to be your even, and most of the ones on the bottom are going to be for odd. So you'll get your clue out. So we'll always ask you, do you got your clue? Try not to, usually they're in a drawer, they're easy for you to access. We're going to be working on the B side first. So we'll grab this one. Once you take this cover off, this kind of fits really nicely here. So we're going to grab a piece of your patient setup. So now you know why these might be in a different location, because your service engineer uses them. And usually you'll have a few tools on site. All you need is a set of Allen wrenches for the most part to do service on this. So usually if I'm working with more than one person, I'll pin the gantry. And what I mean when I pin the gantry, there's a mechanical pin that will slide in place and it locks the gantry in the 4 quadrants. So 90, 270, 0, head up, head down. So you can't rotate the gantry. Why that's important is because I'm going to take this cover off. And if you rotate the gantry, it'll slide off. So what I do in this case, I'll just hit one of these paddles. I hit this one. You guys, some of the paddles don't work. So that put this red light on. That means now when you grab a pendant, you can't rotate the gantry. To change a motor, you don't always have to take this top piece off. But if you have to replace a T-nut, you will. I bring myself a little tray so I can stick all my pieces in. So that's why this cushion is so we don't damage the fiberglass, keep it nice and pretty, and it just rests perfect. So now I have this off. Another safety precaution you want to do is you want to close the jaws, because what's below the jaws is that Mylar mirror. If it's an older mirror, say 2-3 years old, anything you drop on it, it'll make it's Mylar, but it'll just shatter. So you have a lot of tie wraps on here, you got little components, they're really fragile. So once you start playing in the head, those things start to break, and you may break one of those tie wraps. You may not see it, but there's a piece inside the head. So sometimes you guys are rotating the gantry and you'll tell your engineer, he goes, I hear something moving in the head. Well, that's kind of important because it'll fall down, and it always falls and hits the mirror. Everything else it'll miss, but it'll hit the mirror. So you always want to close the jaws when you take the cover off. So you can grab a leaf. They're mounted in fairly stiff with the leaf screw. At this point, if you turn the power off, you'll have to reinitialize. But since we're going to play with disconnecting things, we'll shut the power off. We can turn it on. We don't have to initialize. We can use the service panel to move any leaves. Another safety precaution I use is, and would probably be a good habit for you guys to get into, if you're going to do any service on the MLC, change a motor, always put a towel in here. And it's not so I don't get anything dirty. It's to catch the screw when you unscrew it and you drop it. Because inevitably when you drop it, it's going to fall down to the side and it's going to be right down in here. So then you have to pull off the top cover. So that's why I put the towel in there. Let someone grab a towel and stick it on that side. And you just want to kind of tuck it over the lead and into the lead so it just holds it. And then this is where, you know, if you're more than one person in the room, you want to communicate to the other therapist. You got your hands in there. You shouldn't have the pendant in their hands. You don't want to move any of the jaws while your fingers are in there. So it's just a precaution. This one here, we know we have a problem with leaf B4. So you'll grab the clue for the B side. and it just kind of sits here. It lines up all of your leaves and your connectors. And we'll come up here, we'll grab an Allen wrench. Okay, so that is a 3/32. I usually grab 3 because I forget. So you're going to come up here, and this one says that motor is under 2 screws, so now you have to remove 2 of them. Okay, these are special screws that have a shoulder on them so it doesn't fall out. You'd have to completely unscrew it from the motor keeper. Okay, so now we have the retainer off. If you squeeze or push on these motors, in the drawing you'll see a spring. So you're feeling for the squishiness of the spring. That means the motor So I just gently grabbed the connector or the cable and just pulled the connector off. So here's the coupler. So if that coupler doesn't fit in the groove, it won't be springy. It'll be stiff. So you always want to make sure you stick that in there, and you can you could take this and you can turn the motor by itself and you'll see your leaf move in and out. So you guys have your spare motors. So they'll be in wherever you keep your spares. Some of you will put them in a drawer because you replace them a lot, or they'll be in another stand-up cabinet. Okay, so here's the new motor. You're going to have a protective cover. You take that off. Notice there's no coupler. So you have to take the coupler off the other motor. And it just pulls off. But if you look at the coupler, there's a flat spot. And look at the motor, there's a flat spot. Want to match the flat spot together? Okay, I lied on this one. It's on your half leaf, there's a flat spot. Oh, there it is. Okay. So I got it in the flat spot. That means it won't spin inside the coupler. So also when you take the motor out, you want to spin it, and you're listening for a crunchy sound. That's one way to tell that your old motor you pulled out is bad or it stopped working. Inside these motors are little brushes, and they'll fall off inside and they'll jam. So your motor will spin one direction but not the other. Okay, so then you want to match it up with the tangs of the coupler. Okay, so it's springy. I know I'm in there. And if I want to make sure, I can take it and I can start rotating the motor, and you'll see the leaf move slightly. It's moving, but you got a lot of turns before it'll move a millimeter. So now to put the screw on, even though this is the one I replaced, these may have moved. Need to make sure that they're all springy. Let's see. Okay. So now I know that they're all in the proper position. I can put the screw nut back in. And beforehand, you might want to just push gently on the back. And you adjust it till it's snug, not over tight. You'll break the screw. They're not very big. So there's that one. Now I have two motors off, and I might not know which one goes where. So that's where you can look at the clue, and you can follow the wire. I say, okay, this one is motor 4, and 4 gets connected at the lower one. I also have 6 disconnected. That's this top one. Again, I want to check to make sure it's springy. So it may not always line up with the connector right away. This one I need to turn it slightly, so just go ahead and bend the cable into position. And these are keyed. It only goes in one way. Okay, so they're all connected. I can turn the power on. Come up here. I can move the motor. Works fine. I know that I also pulled out 6, so I'm going to check that one too. Okay, that one moves fine too. So then you can put all the covers on, or you can initialize with it in this state, and that's what I would suggest. But you always have to put the switch back to 0 so the lights are off, then go initialize. So who knows how to initialize an MLC on the hyperterminal? Okay, this is version 7 or above software. So with that version, there's a shortcut. It's called WR. And we'll go in the room. We'll see what we have to do to initialize. So this is hyperterminal. Usually you'll have treat running. So one of the things I did, I'm in service mode in the Linear, and why I did that is I needed to override flow and pump. So it's quieter in the room. I turned off the pump breaker so you don't have that loud noise. But I can only do that in service mode. Okay, so you'd be in treatment mode, and we want to get to hyperterminal. So hyperterminal is down here, usually running when you start up your system. So you can click on that, and it'll come up. So whenever I get into this screen, I just hit the keyboard a few times. That makes sure that I get movement in the window, since you share the same keyboard in between computers. Type in the command WR. What that is doing is rebooting the program that's actually on this workstation and goes over to the controller. So the controller looks at the workstation for the program. And this just shows you that communication link. And once the system establishes communication, you'll see your leaves up here. Okay, so now you're actually seeing what's happening during the communication. So what it just did is it moved the leaves, or the carriages, off these little switches that are inside the unit. Moves them off and comes back. That tells the system where the carriage is at. Now it's just moving the leaves to make sure I'm telling all the leaves to move forward, and the computer saying, yes, all the leaves are moving forward. Okay, down here it says moving out of beam. So that's that optical beam that it's looking at. And now it's going to go through leaf pairs, and it's going to go through each of the leaf pairs. It's going to break that beam and retract. And that's going to tell the MLC exactly what position those leaves are at. And it takes twice as long if you're watching it. So part of our troubleshooting that we'll ask you to do when you're playing with the MLC, or you have a problem, it stopped functioning, is to go look at hyperterminal. A lot of times it'll give us a coded message. Or it might say leaf B26 failed to move, or you have a secondary feedback problem or something like that. That could help the engineer, because he's going to know exactly what parts you have on site. And if you have a part that he thinks the problem is, maybe he'd stop by another location and pick up the part, so when he comes in, he has the part he needs. So now what it's doing, it's closed the leaves, and it's running each leaf pair, and it's testing how good that spring is that was in the system. Now what it's doing is it's checking to see that the soft pots, or your secondary feedback off those motors, is matching the primary of the motor itself. Okay, so we lucked out. That was a bad motor. We replaced the motor. That resolved the problem. This morning it wouldn't initialize. So now we'll go back in the room and have each one of you pull a motor out and put it back in. And we can do 2 people. We could have 2 people at a time do the A side and the B side. Okay? just going to use the easy motors. We're just going to grab ones on the ends. One thing you need to be careful with, if you see the ones in the middle, they're kind of a diamond-shaped motor retaining screw. A lot of times you can get the connectors, these ribbon cables, underneath that screw, and then when you tighten it down, you short out the motor, and it does all kinds of weird stuff. So that's one of the things, if a customer of mine replaces their own motors, they're having issues, I'll come and I'll make sure I don't see any of those ribbon cables underneath the screw. Okay, 2 volunteers. Okay, so we're just going to we'll just do the top one, and we'll do 3 on both sides. It doesn't have to be close.
So how do you read this thing?
So here's 3. So you come back here and it's going to be this top one right in the corner. And then the ribbon is going to be right up at the top.
Yeah.
We can just pull this so you get it. So first thing we want to do before we take any connectors off is turn the power off. That's all right. That one.
Is there a special way to get this up?
Just grab it right by the end of the connector, and you can just wiggle it side to side.
Save this. Are we actually going to change it?
You're not going to change it because these motors are about $150 each. Times 120. So you see this part here, and when you look in the hole, you'll see the display, the tangs. That's what you want to make sure you get that inside the tanks. So which one did you take off? That one, yeah? So if you pushed in them, do you feel the squishiness?
Yeah.
Okay.
Do I undo this one?
Yep, go ahead and take that off.
Do I just pull on it?
And just take it underneath, close to the connector, and you can just wiggle it side to side and it'll come right off.
Gotcha.
Another thing to look at for the motor, if it looks wet,
Yeah, it does have a little bit.
a lot of times, hopefully you didn't have a patient that had an accident on the table, because then you might have a lot of them that are wet.
We don't.
But there's a transmission fluid inside the motor, so it's a little oily. If that leaks out, that's another indication that your motor's going to fail. So did you put it back in? And the screw?
Does it? You're saying if you turn it a bunch, it'll move eventually?
Yeah, so you'll take it and you'll pull it out. You got to kind of have to rock it to find that. There it is.
You'll find a groove that goes into it.
Yeah. Oh, you're leaning. Yeah. Who wants to go next on this side? Okay, let's do number 2. It's on the top. And you checked all the other 3 motors to make sure they were springy when you screw it back on?
Yeah, I checked.
Roger, you're up there, man.
All right.
Yep.
What am I doing, number 3?
Let's do number 2.
Number 2.
Huh?
What's supposed to be springy?
When you put the motor in, and if you're in the groove, you'll feel it a bit springy as you push it.
Does it matter if you screw it back in before you attach it, or?
It doesn't matter.
Is that a magnet?
Yes, it is. So before you tighten it all the way down, check all the motors around it again. Okay, once you get yours in, Roger, we'll go ahead, we'll turn the power on, and we'll make sure that leaf 3 and 2 move okay. Good work.
Your turn.
Easy.
It was easier than I thought it was going to be.
The ends are much easier than the middles.
Yeah, I was gonna say, yeah, exactly. Looks like grip something at that point. You can see why you put the sheet there to help. Yeah, because I can easily see it.
Because Murphy's Law tells you it's always falls down the
Yeah,
side.
exactly.
That used to be my last name and it haunted me.
Murphy?
Everything, all went wrong.
Murphy's not scary as long as you know he exists.
Yeah. Once you know you're just always going to have bad luck, you're just used to it.
Were you testing our theory, Roger?
Yes.
So that theory.
Why do we have to bring up Murphy?
I know.
You have another one?
Maybe.
Let's make sure this towel's in really good. Thank you, my friend.
You're welcome.
I'm gonna let you do it.
So now we get to see how to collect one back out of there.
Yeah. Okay. So go ahead and turn the power on. Roger. Flick it over to the A side, the switch here.
Yep.
Okay. Which motor did you replace?
I did number 2.
Okay, so do the 2s.
Huh?
Okay. And we want to extend it, so we want to move it up.
So push
This one up. Push it back. That's good. That's good.
Okay.
Okay. And we did 3, right?
Yes.
So why don't you do 3?
They sound different. Like normal.
Normal.
Okay.
Different motors. One might be newer than the other.
Gotcha. I did 3.
You did 3? So go ahead and switch it over to this side, the B side. This one. Over. over again,
Okay.
and go up, and then back. That's good. That's good. That's it. Yeah. We're just testing to make sure it moves. When it initializes, it'll put it all back into position. Go ahead and test 2. Okay. So you have, this is 120 leaf MLC. You have 60 on each side. So how do you move the carriages? So on this system, you go to 61, and that'll let you move the carriage. Okay, let's go with motor 6 and 6. And one thing you want to be careful with the motors, they don't work so well after you drop them. So, I mean, if you drop a motor, I would still stick it in and see if it worked. But just keep that in mind. Don't drop the motors. No, that's actually a good question, because you'll
These things will happen.
you'll hear this scenario quite a bit, because there's a lot of screws in there, and all of a sudden one will come loose, and your patient will say, "Something's rattling in there," and
Yeah, right away.
yeah, and so you'll go through, and some of the hardware just comes loose by itself.
Of course.
Or I mentioned these tie wraps, they get brittle, they'll break off, and if you got the head of the tie wrap, the thick part, makes a lot of noise because it bounces around in that fiberglass. And you know, it's kind of disturbing for the patients to hear that rattling sound.
Sounds like something's important.
It does.
Yeah.
But then eventually, where that always ends up is in the high voltage, and it shorts something to ground. Because that's what happens.
That's what happens.
On the part where it shows the MLCs, can you load up a field and then press initialize on there as well? Does that do the same
You can.
procedure?
So in treat, it'll say you'll have initialize and it'll have park. And then also on treat, a lot of people forget that if you have an MLC problem, if you right click in the MLC box,
Yeah.
it'll let you download all the logs. So you right click in there and you say capture logs. It captures all the logs of everything that happened during that event. And that really helps the engineer, because if not, he has to read through all the logs. If you can say, well, this happened at 1 o'clock and we reinitialized and the problem went away. So now he has to go back to that 1 o'clock-ish time frame and look at those logs and see what happened.
Yeah.
So everyone replaced the motor and tested it, right? Okay.
Thank you.
So who wants to go hit WR and initialize? Let's make sure it actually works. Okay, so this is a good learning opportunity. One thing we haven't done is we haven't switched off the service panel. But it depends how quick the software was if it caught it.
So turn it off.
No, we'll see if it still initializes. Okay, so who did 58 or 59? So we can see that they're incorrect. This one is not incorrect. This one's not springy. So when you tried to tighten it down, it was tight. But the one leaf, this one, there we go, was not in properly. So it prevented you from screwing the retainer screw down all the way. Okay, who wants to hit WR on the keyboard? Everything worked and you're off treating your patients, and we'll call that a day for now.
Thanks,
And
Randy.
I'll get your screw out. Okay.
Thank you.